So what we're going to be talking about, for instance, first is rotational kinetic energy. So still in the rotational unit, now we have to address rotational energy of rotation. Well, let me remind you what our kinetic energy formula was before. It's 1/2 mv squared. So you take 1/2 the mass of the object times its speed squared. Definitely will be on exam number 2. Now, let's first of all rename it. We'll call this translational kinetic energy. That's the old stuff. Why not the linear kinetic energy? I have no idea. That it would be the same thing. Linear and translational mean the same thing. It's all our old physics. They just, for some reason, call it linear for some things and translational for others. So that we don't confuse it with the new thing, which is going to be called rotational kinetic energy. You could call it angular kinetic energy. It would mean the same thing. Angular and rotational mean the same thing. It's all our new stuff. From the end of homework 8 on to homework number 9. I have no idea why they call it rotational instead of angular. But that would be the same thing. And just to dispense with any kind of annoying derivations, all I'm going to do is I'm going to replace everything in the formula with its rotational version. So it turns out that that answer is correct. Not that that's something you should do kind of cavalierly, but in this case it's correct. So I put 1/2. What's the rotational analog for m? I. What's the rotational analog for v? Omega. So that's correct. That is how much energy something has due to the fact that it's rotating. So, just like on the linear side, if you go faster or you have more mass doing it, those are both things that make you have more kinetic energy, right? So that's exam 2 stuff, right? So, do you know that a car going 50 miles an hour has more kinetic energy than one going 2 miles an hour? You also know that mass matters, right? If you have a Mack truck going 50 miles an hour, that is more energy in it than a mosquito going 50 miles an hour, right? So mass and how fast that mass is going matters. Same thing over here. If something is spinning faster or it has more rotational inertia while doing it, those are both things that would tend to make the rotational energy larger. So these are 2 different places where you can tuck in energy of motion. Okay? So, say something like this wheel. It could have kinetic energy from the fact that it's just flying through space, translating. Or it could have energy in its motion due to just spinning in place. Or both, right? So there's 2 different motions that you can have. If you're a point particle, you can only have one kind, right? You have nothing to you. So the only way you can have kinetic energy is by moving through space. Translational motion, the old stuff. But if you have an object that has size and shape, it can have energy of motion simply by spinning, right? There's energy there too, motion energy. So, let's talk about, and I guess I should mention that this is VCOM, right? So that's always the ambassador for the entire object for all the old physics, right? We learned that the center of mass is that one point that behaves as if all the mass were concentrated there. So the point I was just making is that VCOM and omega are generally independent. Okay? And I just showed you several examples of that. You can have something that's not spinning at all, but its center of mass is moving. So that would be an example of something that had only translational but no rotational kinetic energy. You could have something that is not moving at all, but it is spinning in place. That has only rotational and not translational. Now again, so that you don't get the misimpression that when one is 0, the other one is not, of course you can have any combination. They're independent, right? Here's an example. You can have something that's spinning fast, but translating slow. Okay? Or you could have something that's spinning slow and translating fast, right? Any combination is possible, right? There's two places to tuck away the energy. You may have one or the other or both. Okay? They're generally independent. But I want to focus in on a particular kind of motion where you have both kinds of energy. So you have both the center of mass moving and there's some rotation around it, which is very common, called rolling. Okay. So think about what happens when something rolls. When something rolls, its center of mass is moving, but it also is rotating around that. You have both kinds of energy. And also, then they are not independent, because when something moves faster across a surface, it also rotates faster. And when something moves slower, it also rotates slower. There seems to be some kind of connection between the two types of speeds when you're rolling that you don't have to have necessarily when you are doing whatever else. So for instance, if we had something that's rotating, like this guy, but in place, then this is not rolling, right? That did not roll properly. So, let's find out something called the rolling condition. There is some connection when you're rolling between these two, and we aim to know what it is. We know, at the very least, that when you spin faster, you move faster. Those two are tied together. I just showed you that on the table. When something is moving faster, it also has to roll faster, or it's rotate faster, or it's not properly rolling. So what I need to do next is to derive what's called the rolling condition. What is the relationship that these two variables have to take to each other when you're rolling properly that they don't generally have to take if you're doing something else? They're generally independent, but in rolling they're not. So let me draw something that's rolling. Here I have a surface. I have something that's rolling. Whoa, that went really wrong. That's not going to be a round object, is it? Let's try it again. So let's try to, as best as I can, draw a round object. Well, it's still kind of egg-shaped, but maybe you can do better. Let me draw the column here. So it's moving forward and it's also rotating. So then it'll roll. And what I'm going to do is I'm going to imagine that I am sitting at the center of this rotating object. So I am right here. Here's my head. So I'm sitting there, and just so I don't get dizzy, I'm going to imagine that I can somehow magically stay looking down at the ground, okay? So what am I going to see? First, I'm going to see the ground coming past at the column. Hopefully that's not a surprise, right? If you're driving forward in a car at 50 miles an hour, it looks like the scenery is coming at you at 50 miles an hour, right? So, but if I am not rotating with this thing, I'm also going to see the thing going around me, right? So I'm going to not only see the ground rushing past, I'm going to see the object rotating around me. So, what am I going to see? Let me take out another color just so it doesn't get too messy. I'm going to see that this part of the object is going like this. I'm going to see this part moving faster, and I'm going to see this part moving even faster, right? Something like this. We talked that that was the nature of a rotating object, right? That points on the edge have a faster linear speed. That's why the big kids always ride on the outside of the carousel. Okay? That's where you get the most thrill, biggest rush on a carousel. Okay? both get to sit toward the middle where v is smaller, right? So we have an equation for these v's. The equation for that is that v equals r omega, right? And we pointed out, of course, that omega is fixed for the whole object. All of the object. And we found, of course, that's the best way to characterize a spinning object in the first place, because all parts of it sweep out the same angle in the same time. It's the v's that they disagree on, right? Because if your r is bigger, right, you're further from the edge, then your v is bigger, right? That's what this equation tells us. If omega is the same, but r is bigger, v is bigger. So, so which point is going to be moving the fastest again? The edge, okay? So if I wanted to, let's call the outer radius of this capital R, as we've been doing, and then if I put in capital R, I'll get the maximum speed, which is the speed of the rim. So, what next? Here is my supposition. V rim, which is this one, V rim, which is the speed of the edge, has to be the same as V com. I try to draw them sort of the same length. In fact, they have to be exactly the same length. Why do they have to be the same length? Well, let's think about what would happen if they weren't. What if you had two surfaces that were moving at different speeds? What happens? They slip across each other, right? If one is moving slower than the other, they slide against each other. Now, there's nothing wrong with that in general, but surfaces can slide across each other, but that's not what happens when you're rolling. When you are rolling, any given part comes down, touches, then lifts. Right? That's the nature of rolling, is you come down, you touch, you lift. You don't slip. Right? That's what rolling is. It's a strange state where your object is coming down, touching, lifting, but instead of sliding, it's just the next part of the wheel that comes down, touches, lifts, right? That's the nature of rolling. There's no sliding, okay? When an object is rotating, it's important that the ground comes by like that, at the same speed. If it doesn't come by at the same speed, then you're slipping, and that's not what rolling is. In fact, sometimes they call, another name for the rolling condition, which we're deriving, is the no-slip condition. It's about how do you roll without slipping across the surface, because proper rolling, there is no sliding of one surface across another. So, where does that help me? It helps me because now I can say that these two are equal, and I plug in V com here. And I'm done. Because now I have my relationship. V com equals capital R times omega. I said there should be a relationship between how fast the center of mass moves and the rotation rate, and there it is. I said that when one is bigger, so should the other, and that's certainly the case, right? In fact, they're directly proportional, which means that if you want to move twice as fast, you have to rotate twice as fast too, in order to maintain proper rolling. Now this right here may not look like much. It looks very similar, of course, to the original equation, but be careful, it's not. This is only true for rolling. The original equation was true for any rotating object, but there is no guarantee that, generally speaking, that the speed of the rim has any relationship to V com. That's only true when you're rolling. If you need further evidence that this is not always true, look at these. Look at these previous cases. Here V com was 0 and omega wasn't. That doesn't satisfy this. Here V com wasn't 0 but omega is. That doesn't satisfy this. That's okay because these aren't rolling. This is. Right? This has to be obeyed when you're rolling. Okay? when you're rolling, there is a relationship between the center of mass speed and the rotation rate, omega, angular speed. All right? Now this does bring up another thing that's really important about rolling. I mentioned this nature of the fact that a wheel comes down, touches, lifts off. There's never any slipping. We call that kinetic friction, right? Now kinetic friction takes kinetic energy and sends it to what? Heat. So if you're rolling, it does a lot to make sure that you don't lose energy to heat. Let me give you an example. If I take this object here, this disk, and I slide it, it's no surprise that it rapidly comes to a stop because kinetic friction steals that kinetic energy and turns into heat. Okay? If I give it a nice modest push, it doesn't go very far. If I roll it, it can easily make it to the end of the table and beyond. So rolling is a way to guard against friction. Now we like to make fun of the cavemen. Like, couldn't you really think of a wheel? Was that really so hard? Right? There's all these cartoons where they're trying out square wheels and trapezoidal wheels. They haven't figured out that it should be a circle yet. But in another sense, a wheel is an amazing invention. Okay? They didn't always have wheels, and life was a lot harder before they had wheels. Now, if I told you there was some magic device which would allow you to go across a surface that is far from frictionless and yet not lose any energy to friction, you'd say, that's crazy. But what is it? It's a wheel. Okay? So if this was a perfectly flat surface and there were no air resistance and I had a perfectly round wheel and I set it loose, it would go forever. Okay? That's pretty amazing. Now obviously that doesn't happen with real wheels. Why not? Well, reason number one, air resistance. Can't do anything about that. You're still going through the air. Number two, it's impossible to make a wheel perfectly round. Okay? Any wheel will flatten. You probably know, like imagine a bike tire, right? It flattens when you weigh it down, right? So it goes flat a little bit or a lot depending on how much air if your air tires are properly pumped up, right? And think of a bicycle wheel or a wheel of a car, it flattens, right? If you took a snapshot of it, you'd see that the wheel is slightly flat. Well, that's where the energy gets lost. It's impossible to keep a wheel perfectly round. You ever take a paper clip and do this until it breaks? Yeah? Okay? You ever touch the tip, so right after it breaks, what do you notice? It's hot. Where did that energy, the heat, come from? The internal flexing. Well, that's what happens in a wheel. It flexes as you flatten out different spots. That's where you lose the energy. It's because you can't keep a wheel perfectly round. You also, if you have any vehicle that is based on a wheel, at some point, you're going to have to attach it to something that is not rotating. Otherwise, if you're rotating with it, you're going to get very dizzy in that vehicle. So at some point, you have to attach something that is rotating to something that is not. So think of like a skateboard axle or something like that. What do you notice here? That's where you get some friction. Regular old kinetic friction. Unless you try to use the same principle that prevents friction losses like this in miniature. Those things called ball bearings. There's these little tiny spheres that you put between the axle and the wheel. And they roll around, and in miniature you get the same idea. Right? There's lots of things you can do to minimize frictional loss. But for our purposes, since the frictional losses when you're rolling are so minimal, we're going to basically neglect that. We're going to pretend that there's no frictional loss whatsoever. And remember, this is a far from frictionless surface. But when you're rolling on it, rolling guards against losing energy to the environment. So this is basically factoid number one, factoid number two about rolling. Let's go over here, write down things that are true about rolling. When you're rolling, The non-conservative work we approximate is 0. Vcom is equal to r omega. And I want to add one more thing to the list. And let me make a little box so that I can put the final result in that box. And you're going to be very happy to have this final factoid. It's going to make your homework 10 so much easier to have it. So let me show you. Are there any questions, by the way, before I do that? Okay, so let's knock it out. So we mentioned that when you're rolling, you have both kinds of kinetic energy. Let's find an expression for the total kinetic energy. That consists of both translational and rotational parts. And let's plug in our formulas. 1/2 mv com squared plus 1/2 I omega squared. That's nothing remarkable yet, but let's plug in some stuff. First of all, I know that when I'm rolling, Vcom and omega aren't really different, not really completely independent, right? We just said there's a huge relationship. So let's just pick one and get rid of the other. So here I'm going to plug in omega is Vcom over the radius of the object. That's my rolling condition, right? So that's one thing I want to put in, and of course the moment I put that in, this what I'm about to get is only true for rolling, but that's what I'm looking to get, right? I'm looking to get things that are true for rolling. Here's the other thing. I'm going to plug in for the rotational inertia. Now you may say, why would you want to do that? Don't you want to leave open the possibility that you can have any object rolling? Well, yeah, we do want to do that. But here's the thing. Not every object can roll. Only round objects can roll. Right? If you look at all the rotational inertia values on that second page of your formula sheet, a lot of those are not rollable. Okay? But you will notice for anything that's round, all of the rotational inertia values have a common theme. So if you look, for instance, at a solid sphere, the rotational inertia is 2/5 mr squared. A solid disk is 1/2 mr squared. A thin ring is mr squared. It's always blah, blah, blah mr squared. So that's the common theme. If you have a radius, your rotational inertia will be something mr squared. And I'm going to have as a stand-in for that something, squiggle. It's some Greek letter, I forget the name of it, so I'm just going to call it squiggle. Squiggle is a stand-in for some numerical value, 1/2 or 2/5 or 1 or whatever. It depends on the particular object, and I don't want to commit to one. But every round object has a rotational inertia in this form, so I might as well plug in as much as I can. So squiggle, again, is just a numerical factor, which is sitting right there in front of the rotational inertia of the object that you have. You just look on the formula sheet to get it. Okay? So this is just a number. All right, let's plug in. I have, let me see what first comes out of the rotational inertia term, or the rotational kinetic energy. That's 1/2 times I times omega squared. So let's plug in. I have my squiggle mr squared, and I have my v com over r. So let's see what I get. This r is going to get squared, and it's going to cancel with this one. Right? I'll pull squiggle to the front, just because. I want to see what else is left. What is that thing in parentheses?
Kinetic energy.
Translational kinetic energy. This is a fact that you definitely want to know, is that when you're rolling, your rotational kinetic energy is just squiggle times your translational, where squiggle is some number that is particular to what object you have that's rolling. That is amazingly convenient fact. And I will warn you, it is not on the equation sheet. You're going to want it. It's not on there, so everything that is, the ingredients are available. The formula sheet will tell you that 1/2 I omega squared. It'll tell you the rolling condition. You can look on the equation sheet and realize that all of the rotational inertias look like this for round objects. I don't think it's too much to ask you to plug them in here and show me this. So if you want, say, full credit on the final exam, you can't just write this down. You have to show me this 1 or 2 steps to get it. So rolling, another thing you're going to want to use, which is amazingly useful, is this. And going along with that, of course, if you wanted an expression for the total kinetic energy, that's going to be your translational 1 plus squiggle. So the 1 takes care of the translational kinetic energy, and the squiggle takes care of your rotational. Is that okay? So that box is invaluable for tackling any problem where something is rolling, and that's just what I'm about to do. I'm about to do an example problem where we use something that's rolling, and we're going to grab liberally from that box. Okay? Are there any questions before I do that? All right. So here's my problem. My example problem, I'm going to have a race. I actually brought it with me. You're going to be able to see it with your own eyes. Here's my contestants. It's a disc and a ring. Okay? I'm going to have a race. Here's a solid disc. Here's my thin ring. Here's my incline that I'm going to race them down. I'm going to say that the incline is of a height h. I'm going to say they both start at rest. And just to keep it fair, I'm going to assume that they have the same mass and the same radius, although we'll find out later if that's even important. And I'm going to ask, how fast is each of them going when they reach the bottom? Now, that of course only tells me who got there going faster, not necessarily who got there in less time, but in this case, one implies the other. Because if you got here going faster, that means you also had a larger acceleration, right? If you had a larger acceleration, you also got there in less time. So if vcom is larger, that also tells me that the t was shorter. Okay? So I had to dip a little bit into the old kinematic stuff. Of course, the energy stuff doesn't include time. So that was one of the major drawbacks of the energy method, right? Can't find time. If on the final exam you get asked for time, then give away what method to use. Energy is not going to work. So in this case, since I plan to use energy, I had to think a little bit about how getting there faster means getting there sooner. Okay? Getting there going faster means getting there sooner. So I'm going to use vcom final as a surrogate for figuring out who the winner is of the race. So let's set it up. Start with my master energy equation. Always a good place to start. And because I'm rolling, straight away, I'm going to plug in non-conservative work is 0. So that's borrowing one thing out of the box for rolling. I'm going to assume that they roll properly. Here I'm going to plug in kinetic energy initial plus potential energy initial equals KE final plus PE final. my classic energy conservation. Where might I pick my h equals 0? What would be a good spot for it? The bottom, right? Usually want to pick the lowest side of interest, which means that the final potential energy is 0, the initial is mgh, right? So we think of it as giving up all your potential energy into kinetic by the time you reach the bottom. That's all should be very familiar, right? The only new thing is the fact that as these things go down, they're not just going to move, they're also going to rotate. So they're going to roll. So I go ahead and I put in my expression for total kinetic energy. So I have, initially, they're of course stopped, so I don't have anything, but at the bottom, I'm going to have to acknowledge that the kinetic energy comes in two forms. So I get mgh initial is going to be 1/2 m become final squared 1 plus squiggle. So whatever that initial store of potential energy that each object got, they're going to have to split that between the two kinds of kinetic energy, right? Because when you're rolling, you have both kinds. Now, by the way, I have yet to plug in a single thing that isn't true about the disk or the ring. So I'm going to try my best to avoid that, because the moment I plug in something that's true about the disk and not about the ring, my calculation has undergone cell division. Now I have two columns, right? Now I have to work two problems at once. Let's not do that. Let's try to work smarter, not harder, right? Let's try to only plug in things that are true about both of them, because then I can avoid having to split my calculation into two sides. I haven't plugged in anything yet that isn't true for both of them. Now, let me make a point about mass. If you have more mass, you'll have more kinetic energy, but guess what? You also get more mass at the beginning. The mass cancels. So they don't have to have the same mass. They can have different masses and the result's the same. Let's solve for become final here. That's going to be this. At this point, I'm pretty much come to the end of the road of saying things that are true for both of them. At this point, I have h in there, which is a given, so that's fine. And then the one remaining piece, of course, I have is squiggle. Squiggle is going to be different for both objects. But I do want to mention that r isn't in here. So that doesn't matter either. They don't have to have the same mass and radius. Where did the r go? The r actually canceled way back in my derivation of this equation. If you look, the r went away. And anytime something cancels, it means it doesn't matter in the answer. Okay? So, at this point, I've incorporated all of this information. I've plugged in non-conservative work is 0. I've used, of course, my total kinetic energy equation. And this, of course, incorporates this. If you look back to how I got this in the first place, I involved plugging in the rolling condition. So the rolling condition is now redundant for the solution, although you can, of course, pull it out at any time. For instance, if you got VCOM, you want to get omega, you need to use it. So let's go ahead and plug in. At this point, I'm going to have to split this into two, one for the disk and one for the ring. So we go ahead and we look at the equation sheet. The equation sheet will tell us that the rotational inertia of this around its center of mass is 1/2 mr squared, and this one is mr squared. I mentioned that on Monday. You don't need to know exactly why they're those, but you should understand why the ring is bigger. Can anyone remind me why the ring had a larger value?
Mass distribution.
Mass distribution. Exactly. The mass is all on the outside, so it's more stubborn to rotation, right? The solid disk, the mass is more, on average, in toward the pivot, so it's easier to rotate. So let's go ahead and plug in. For the, let's do for the ring first. What's a squiggle for the ring?
1/2.
For the ring? 1, right? If the rotational inertia is squiggle mr squared, here's just mr squared. So squiggle is 1. For the disk is 1/2. Exactly. All right, let's plug that in. Square root of 2gh 1 plus 1. Okay? 1 plus 1 is 2. That cancels with this 2. And I get an expression, square root of gh, which, of course, if you had the height of the incline, you could crunch it into a number. But that's not going to help you determine who wins the race, any more than if you had a race of 2 people and you only got told 1 time or 1 speed. How does that help you? You need to compare, right? So we need to plug in and see how does the disk compare to that, right? So let's do that. So it'll become square root of 2gh 1 plus 1/2. 1 plus 1/2 is 3/2, right? 2 over 3/2 is 4/3. So that's your answer for this. Now, if your intuition about the square roots of fractions is not that strong, the square root of 4/3 is 1.15. Who wins? Disk. It ends up being 15% faster, right? Instead of square root of gh is 1.15 times that. It's not a total rout here, but the disk is going to win that race. Okay? That is our prediction. All right? Let's try it. Here's our contestants. Trash talking before the race. Okay? We know, we've calculated by physics, that there can only be 1 winner. This isn't an incline, so let me tilt the table so it is. Here's our racetrack. Here's our contestants. We have calculated that the disk should eke out a win. It's not going to be a total blowout, but it is going to be going 15% faster when it reaches the bottom. Let's try it. It wins. Ring wants a rematch, doesn't think there's something wrong with that side of the track. Okay, let's try it again. The disk ekes out a win, right? So, we've shown why it is mathematically. Can we reason it conceptually? Yes, we can. Okay? So if you've ever been out at a playground and you saw the kids are having a foot race, and you have the little wiry kid ready to race against the biggest kid in the class, you know who's going to win that race, right? Little wiry kid's out of it. Okay? Big kid's got a lot of inertia. It's hard to get going from the starting line, right? Okay? Well, this is the rotational version. Okay? The ring has all its mass on the outside. Okay? So it has a large rotational inertia. That's a disadvantage when you're trying to get going, right? In general, you're going to have to a lot more energy to get it to rotate because it's so stubborn. Its mass is more on the outside. This, it's nimble, right? Right? Its mass is more toward the middle on average. It's more nimble. So that's what we have. So what happens here is that the ring has a certain allotment of potential energy, and it is going to have to spend a lot more energy towards rotation, but guess what? That means less for translation. So it allots its initial pool of energy in a different way, right? It has to put more towards rotation, so it has less available to actually win the race. You spend so much energy getting rotating that you don't have enough to shoot down the incline. Whereas the disk might have the exact same amount of energy to start with, but it doesn't have to spend as much towards rotating, so it can spend a lot more of its energy translating. It's about how you use your energy. You have an initial pool, but from there, how you draw on that energy, one form of kinetic energy or the other, may not necessarily be the same. In fact, you can see it's right in the equation. If squiggle is larger, right, then VCOM is smaller. Remember what squiggle is, right? Squiggle is the multiplier in front of the rotational inertia. What this is really saying is that the larger rotational inertia you have, the worse you do in the race, right? Larger rotational inertias do worse. They have their mass on the outside. There is more effort that has to be expended to get them rotating, which means less available for translating. Okay? It's right in the equation. In fact, if squiggle was 0, because you weren't rotating at all, let's say you had a separate incline here where there was just a block and it was frictionless, that would blow these guys out of the water. It doesn't have to spend any energy towards rotation. If you plugged in that, so the frictionless, you get square root of 2gh, which is 40% faster than the ring. Square root of 2 is about 1.41, right? So 41% faster. That's no competition, because this doesn't have to spend any energy into rotation. It's got it all, keeps it all for translation. Okay? And the more you have to spend towards rotation, the worse you will do, right? Because you have a larger rotational inertia, you will